Sometimes light acts like a wave, and sometimes light acts like a particle. When it acts like a particle, we call that little bit of energy of light a photon. Not a proton, but a photon. As in, ready the photon torpedoes, Mr. Chekhov. So this little amount of light is a photon, and there are photons of different energy. Higher energy light, when it strikes your eye, you perceive it as blue light. Lower energy photon you might perceive as red light. Even lower energy would be infrared, and you can't see the infrared with your eyes, although you can sometimes perceive infrared light as heat. Higher energy light than blue is ultraviolet, and that's the reason you get sunburn from ultraviolet light, is the photons of light carry a lot of energy. With digital detectors like those developed and perfected by astronomers and used in digital cameras nowadays, you can actually see, especially at low light levels, the individual dots produced by each individual photon of light. When you take the picture with higher light levels, it becomes a better looking picture, it's sharper, the picture looks continuous, and you lose the individual dots, but they're still there. Each photon of light has registered in your digital camera and become part of the picture. So when does light act like a particle, and when does light act like a wave? We can see how the wave properties of light work by analogy with water waves. If you allow two waves to combine or interfere with each other, a property of waves is that sometimes they interfere constructively, they add and they give you a bigger wave, and sometimes they add destructively or out of phase and the wave disappears. I just happen to have a handy dripping faucet here, and like any good scientist, when my faucet drips, I pay attention to the waves. So a pattern of waves is radiating out from where the drips hit the water, and the light colors that you can see are the crests of the waves, and the dark colors are the troughs of the waves, okay? So it's pretty easy to understand waves from a single source. If I put a slit into the picture, notice that the slit itself acts like a source of waves. So when water goes through a slit, the waves begin to fan out in every direction. Now let's look at two slits. Here's where it gets really interesting. The waves are coming from this slit and from this slit. So each one is a source of waves. And depending on where you are, the waves might be in phase or out of phase. That means that when they're in phase, the crests of two waves add and you get an even bigger wave, and the troughs of the two waves add and you get an even bigger wave. But in places where the waves are out of phase, the crest adds to a trough and they cancel each other out and the wave disappears. So I think you can see that in this direction and in this direction, the water waves are canceling each other out and the wave disappears. This is a graphical representation of what happens when two waves add either in phase or out of phase. So up at the top, the waves are in phase, and so the peaks get higher, the troughs get deeper, you have a strong wave. If two waves are out of phase, they cancel each other out, as you see in the bottom illustration. Can you actually add two beams of light and get dark? Could you take a flashlight and another flashlight and combine the beams and get dark? What do you think? In order to test that, we should use light of a very specific wavelength, a very pure color. If all the light is the same wavelength, then it should be possible for the peak of one wave and the trough of another wave to add up and cancel out and make dark. On the other hand, if you have the peak of one wave and the peak of another wave add, the light should be bright. So we would predict that if light acts like waves, in one direction you'd see light, and then in another direction you'd see nothing, just like we saw with the water waves. Nowadays, it's very easy to have light of a very pure color. You just use a laser. So I have a laser beam here. We're going to point it at the screen. This very pure color makes a nice bright spot of light. Now what happens if I move some slits into the beam, and this laser beam, instead of one beam of light, becomes more than one beam of light, giving a chance for the different waves to interfere. And here we are, voila! In some directions, the beams add to make bright. In other directions, they add up to make no light at all. So just like the water waves can cancel each other out, interference we call it, light acts in this way like a wave, and light plus light in certain directions can make dark.